Yeah, this is the start, I guess, of a variety of presenters in this particular class. And hopefully you will learn to adjust to different presentation styles, different approaches, things like that. But we're going to have some fun and hopefully learn some things and learn certainly some practical skills that we're going to move ahead with. I'm going to be talking the next 2 days about chart analysis, and in particular something that isn't done that much anymore, especially across parts of the Weather Service, which is subjective analysis or hand analysis, which you may find perhaps a bit unusual in that at SPC we are probably the most advanced in terms of Weather Service facilities in utilizing not just advanced workstations, but also high-resolution model output to help us in our forecasting area. But we've also learned that doing some things that have been a very traditional part of severe weather forecasting can still be rather helpful. So what we're going to talk about a little bit, we're going to blend a variety of things in here. Some aspects of forecast philosophy. We'll be talking more about this, obviously, as the course goes on. Role of humans, some steps in forecasting, the importance of analysis. A lot of what we do, as you know, at SPC is short-term forecasting. While we do outlooks that go out to day 8, we focus much of our attention on the day 1 period, and particularly in the first 6 to 12 hours. If you think of some of our products, mesoscale discussions, watches, short-term outlooks. So a lot of our focus is traditional in that severe weather forecasting as it got started way back in the 40s and 50s. There wasn't any numerical model output. There was just observational data, and all forecasters had to work with was observational data, and that limited how far out in time you could issue forecasts. You had to make your own forecast of what the 500 millibar pattern would look like 24 or 36 hours down the road, and that wasn't easy, because how many of you can integrate the primitive equations in your head? I can't. It's tough to do. So severe weather forecasting traditionally was focused in the short term. So we're going to talk about observational data, some of the strengths as well as limitations of it. We'll talk a little bit about conceptual models that we apply, and a little bit about the relationship between pattern, environment, and severe weather. I think most of you can understand, if you've paid any attention to severe weather forecasting, you can look at a model forecast of 500 millibar pattern and a surface pattern. If you know it's April or May, within about 30 seconds you can say, I think we might have a severe weather risk today in a particular area just based on the pattern alone. And then we can relate that information. We need more than just that, but that can be a starting point. Why do we still do hand analysis? Can't we simply rely on the models for analyses? We'll talk about that some, and then we'll talk about some guidelines, examples, and we'll have some homework to do. So, where do humans fit into the process? This is a big discussion area right now in operational meteorology. There's a lot of talk about forecasters becoming impact-based decision support specialists and providing more information about what the impacts of the weather are going to be to people like emergency managers, utilities, things like that. Will forecasters actually be forecasting in 5 to 10 years the way they're forecasting now? What will their role be? This is, like as I said, active discussion right now. I think we can, though from the severe weather perspective, say that we think the human will have a large role to play for at least the next 5 to 10 years. We shall see as models get better. But one of the things that we do really, really well is we can take information from a whole variety of different sources and integrate things in our head. We can synthesize information. We're very good at pattern recognition. There's a number of things that we do well that it's really hard to write code to do the same thing. So some of the things that we can do, and you can see them here, we can apply principles of atmospheric science and conceptual models. You've been learning that in the dynamics classes, obviously. How do we apply that information? QG theory, things like continuity equation, lapse rate contributions, and then different types of conceptual models of mesosystems, supercells, etc. We're very good at taking a variety of information and putting it together in ways that it's really hard to do in an automated sense. Obviously, as we already talked, computers and code and supercomputers have very good roles on things we can't do. I can't compute moisture convergence. I can't integrate the equations of motion, a whole variety of things. But right now, we should be using those not to just give us the answer, but to enhance our understanding of what's taking place. If we essentially give away the thinking part to numerical model solutions, what role do we play? We really need to be aware of that. Steps in the forecast process. This was a really good paper that came out in WAF in 2003 by Lance Bozart, professor at Albany. And he entitled it, somewhat of an old English phraseology, Whether the Weather Analysis and Forecasting Process. And what he mentioned is that there should be 6 steps in the process. The first 2 are what happened and why did it happen. What's happened up to now? If you look at a 24-hour satellite loop, what had been going on? What was the evolution of the pattern, the processes to bring us to the current time? And do we understand what's happened over, say, the last 24 hours, last 6 hours if you're looking at radar, perhaps? Do we have a sense of why did we get to the current point in time? If we don't understand how we got to the current point, it makes it more difficult to move out into the future. So then what's happening right now? Analysis of the current, whether it's the latest satellite imagery, latest radar, latest other types of observational data. What's happening right now? And more importantly, why is it happening? Do we understand the physical processes? So 1, 2, 3, and 4 are linked. How did we get to the present time? What are the processes taking place? What's happening right now and why? And admittedly, there may be times that we don't know exactly what's happening at the present time. Why did a thunderstorm develop in one county versus the next one over? Do we really know sometimes? Not necessarily. We can surmise, well, maybe the cap was a little bit weaker in a particular place. But a lot of times we don't have complete information. So this is where we have to use our understanding of atmospheric processes to try and assess what's taking place. So once we go through steps 1 through 4, then we may be primed to move ahead. I know what has happened, how it got up to the current time, and now the challenge is moving ahead in time. So really, if we're going to do a thorough job of this, we really need to go through all these steps. Sometimes we don't. Sometimes forecasters don't. How many of you could take a look at, say, some NAM output, some gridded output, and without even knowing what's going on outside right now, make a forecast for tomorrow, just off the model? Probably could, couldn't you? You wouldn't have to know a thing about what has happened or what's happened up to now. You could just take the model grid straight out, and you can make a forecast. Of course, guess what? You could computerize that as well. And you don't really need to be in that particular role if you don't want to. But would you feel comfortable doing that? Do you feel as if you would really know what's going on? Does the user care? These are interesting questions that you might want to consider. And there are times, in fact, where you may be so busy in a local office or at SPC that you're going to say, gosh, we got hardly any time to do the forecast. We're going to have to skip some steps. But you might not feel as comfortable in terms of what you're issuing. Bozart also talked about why sometimes we don't really see what's going on. Part of the problem is, he listed the number 1, real-time mesoanalyses of high quality are generally unavailable. And we'll talk more about mesoanalysis, particularly on Wednesday, in terms of the smaller scale details and how important they can be for what we call weather, and especially what we call extreme weather in this respect. We have a lot of observations in number 2, but how do we synthesize them? Do we use data assimilation systems from numerical models? How good of a job do they do? If you look on the internet, you can find a variety of surface analyses out there, but usually they're pretty broad scale. They don't have a lot of detail in them. And sometimes they may not even be the way you would analyze it. And the same thing with 4. And a lot of times we can have so much we are looking at, it's hard to grasp what are the important details, what's the important information, and what are pieces of information that on a particular day might not be as important. We can do a heck of a lot of looking, but maybe we're not seeing. So from our perspective, subjective analysis of observational data, we're not even talking about models. Observational data is a key role in short-term severe weather forecasting. So on the left is sort of the funnel, how we go from the larger scale down to the mesoscale, and then even down farther in toward the storm scale. What do we focus on? The relationship between the synoptic and mesoscale environment primarily and thunderstorm evolution. Given a certain environment, what's the likelihood of thunderstorms to develop? Where? What type of storms? What's the intensity? Do they have a severe weather risk associated with them or not? So we have to be aware of the larger scales as well as the smaller scales. And you have to typically start with the larger scales, and that's what we're going to be talking about more today in upper air analysis, where we're starting with the larger scales because those often have controlling influence on what takes place at the smaller scale. The other reason we have to depend on observational data is the third bullet. We're interested in forecasting severe thunderstorms and tornadoes, hailstorms, wind, tornadoes. I can't look at the NAM and say, give me the NAM forecast for the tornado. Where's the tornado in here? I can get QPF out of a model. It's a natural byproduct, so to speak. If I'm forecasting precipitation, that comes out of the models, regardless of the resolution of the model. But do they produce tornadoes explicitly? Not even the convection allowing models we refer to as convection allowing, meaning it can represent some aspects of convective storms, but not all processes in convective storms. That's convective resolving models. And there you've got to get down to probably a half a kilometer grid spacing or less. So we're not really talking about those, but because we're forecasting severe weather events that occur on scales typically smaller than models can replicate or resolve, and smaller than the standard observational network, we have to infer what's taking place on the smaller scales from the somewhat larger scales. And the final bullet is something that we always have to remember, but there can be tendencies and temptations not to. The real atmosphere is more important than the model. And the model atmosphere may not replicate what's taking place in the real atmosphere. But it's very appealing because with model grids, we have information at every level in the vertical, fairly fine horizontal resolution. We have quantitative information all over the place. But most of it might not replicate what's actually taking place in the real atmosphere. We'll talk more about that a little bit later. So, what sort of sources do we have? This is a fairly old conceptual diagram from Chuck Doswell. It's more than 30 years old. And if we look at the top, here's our weather knowledge up at 100%. If we knew everything about the atmosphere, here's forecast hours going out from 0 to 24. On the bottom, climatology is constant. Climatology can be a good starting point, but if we can't improve upon climatology, we essentially have a no-skill forecast. Anybody can issue a climatological forecast. So if we can't improve upon climatology, we're really not helping people very much. But we have one of the things that you notice in here between forecast hours 0 and 9, say, and particularly 3 to 9, we sort of have a gap in our knowledge of meteorology. What's happening in the shorter time frame on the smaller scales can be very difficult to know what's going to take place. The models help somewhat, but not as much. If we try and extrapolate what's taking place, it doesn't hold true for very long. If you have a radar at the current time and you say, I'm just going to extrapolate these storms, 1 hour, 2 hour, 3 hour, just linear extrapolation, it's going to start to break down after a few hours. It's not going to just be something that you can do by tracking things along, because there's going to be some dissipation, there's going to be new development, etc. So it's in this short time frame between 3 and 6 to 9 hours, which for better or for worse is the time frame that a lot of SPC focuses on in terms of the mesoscale discussion and watch time frames. This is where we have to work exceptionally hard. We've had some improvement in terms of the higher resolution models in the last 10 years or so. And you can say, well, shoot, we have a 3-kilometer HRRR. It comes out every hour. It gives us a forecast, even at 15-minute intervals. Doesn't this fill in the gaps particularly well? On some days it helps. On other days it may be misleading. Let me show you something in through this short-term time gap area. And this is some HRRR reflectivity verification starting in 2010, and it's annual verification all the way up to 2015. 2015 is here, this top line. And these are forecast hours going out, 2, 4, 6, 8, etc. This is CSI Critical Success Index on the vertical scale. And one of the things you notice is how the skill drops off very, very rapidly within the first few hours. It really plummets after the initial time in through here. So that while the HRRR can be useful, you can see that area where we have a rapid drop-off in accuracy in the first few hours. So it's helping a bit to fill that gap in knowledge in the first few hours, but we still have a ways to go. And I'll show you an example of this in a little bit. So at this particular point, especially for short-term forecasting, we really have to synthesize information from observations, apply conceptual models, as well as NWP. If we try and use just one without the others, we're going to be hurting even more than we are already. So, importance of analysis. If we really think about this and break it down into basic terms, what's a forecast? Well, you have to start with the analysis and then add a trend. If you're integrating equations in NWP, this is what you're doing. You have to start with an analysis and you come up with a trend. Well, we have to do that too as humans. Remember the 6 steps that we talked about at the beginning. If we don't accurately assess the current state, our probability of making a correct forecast is probably going to be reduced. Current models have difficulty resolving some aspects of the atmosphere that's very critical in convective forecasting. The thermodynamic structure, especially the boundary layer structure, the depth of the moisture, presence of capping inversions, etc. That's where the models have the most trouble. What about boundaries such as sea breeze, dry lines, outflow boundaries? Well, you can see some of that in the higher resolution models, but the chances of them being in the correct location are not particularly good. And then when we talk about convective precipitation, then it gets even more challenging. If you're talking about a model that has parameterized convection, there's a lot of simplified assumptions that are taking place in terms of what happens in the shallow convection and then when deep convection is triggered. What about the convection allowing models where we are not using parameterized convection, but we're getting explicit convection from the microphysics and other processes? Let me give you an example of a HRRR. This was a couple of years ago, but things haven't changed, about evening convection over Kansas. I'm going to show you 5 hourly forecasts starting 18Z, and then we're going to look at some forecasts valid out into the evening. So here's the radar at 22Z. This is the 18Z forecast, valid at 22Z, so it's a 4-hour forecast. In the upper middle is 19Z, 3-hour forecast, valid 22. At 20Z, it's the 2-hour forecast. 21Z, the 1-hour forecast. And here's the 22Z initial time. And it matches up with the radar reasonably well if you compare these two. You can see already some of the forecasts have maybe too much and too strong convection in the northwest Kansas. So I want you to keep an eye on that particular area, and I'll give you a little bit of help because there are going to be some circles on here. This shows we're giving a well-rounded presentation to everybody. So as we move out ahead, this is now the 1 hour forecast valid at 23Z right here. This is the 2 hour forecast, 3 hour forecast in the upper right, 4 hour forecast, etc. You can see the radar. We're going to step it ahead. This is at 0Z. And you can see that the model consistently wants to develop too much and too strong of an area of convection in Kansas. And it's very consistent, which may lead you to think the model's telling me the same thing. It must be right. Not necessarily. It can get stuck down the wrong path just as well. And if we move out to 2Z and 3Z, just within a few hours, every run of the HRRR, the last few hours, keeps wanting to produce the same thing. And it's not correct. So while it's giving us short-term forecast information on convective storms, it's giving us consistent information, but consistently incorrect information. So we have to be careful, even with models such as this, which on many occasions can give us very useful information, but not always.